So, good afternoon, class. And so far in the journey of the complex number, we had dealt with various topics pertaining to complex numbers, and we had seen how we are solving the tedious numerical problems using the complex number techniques. As we are already studies, as we had already studied, complex number it is a combination. It is a combination of two numbers, the real numbers as well as imaginary number. We are just notifying a complex number in the form of z is equal to a plus ib, where a represents the real number and ib represents the complex number. And so far we had discussed in the complex number the various topics which are entitled as addition of the two complex numbers, the properties associated with the addition of the two complex numbers, subtractions of the two complex numbers, and the properties associated with the subtraction of the two complex number. Similarly, the multiplication part we had covered, but there are certain portions are there which are remaining, and we will be covering those topics today. So today we are going to discuss some of the important topics pertaining to the complex numbers, which will be very helpful for us to solve the tedious or complex numerical problems. So first of all, the very first topic is existence of the multiplicative inverse. The existence of the multiplicative inverse. As the name suggests, there is a inverse is there which is existing in the case of the complex number, and we will be saying how we are stabilizing the relationship between the two complex number and how they are the product of the two complex number is one, and how it is established or it is proved that existence of multiplicative inverse exists. So we will see slowly and gradually. First and foremost, we will see how we are stabilizing z into z1 is equal to 1. First and foremost, suppose we are taking one complex number which is entitled as z is equal to a plus ib. Understood? And the second complex number is z1. So z1 is equal to x minus iy. Understood? So it is written here as a plus ib and x minus iy. Now we will see the product of the two complex numbers, that is z into z1, a plus ib into x minus iy is equal to 1. Understood? So in the right hand side that we had, which I had written 1, we can write it here as the real part is 1 and imaginary part it will be 0. So 0 into I into 0. So we can write the right hand side as the bifurcation, or it is a combination of the two numbers, that is real part is 1 and the imaginary part is I into 0. So first of all we will see how we are doing the product of the two complex number. In this case it is ax minus aiy plus ibx minus I square into by is equal to 1 plus I into 0. Understood? So we are seeing here that there are certain terms are there which is consisting or which is comprising of complex numbers. So we will be segregating those terms, and we will be segregating the real part at one side and the imaginary part at other side. So we will see here it is ax, I square is minus 1, I square plus by, I will take common, bx minus ay is equal to 1 plus I into 0. So we had seen here how we had segregated the complex number into real part and as well as imaginary part. Now we will be trying the formula of the equating of the two numbers. Whenever the two numbers are there and they are separated by equating sign, equal sign, so we can equate them with their real part as well as imaginary part. So we are seeing here ax plus by is equal to 1, the first equation, and secondly bx minus ay is equal to I is 0, it is 0. It is second equation. So we had got two equations, the two simultaneous equation. We will be solving those two equations and we will find the value of x and y. So we will be finding the value of x and y here, and we will be substituting the values here, and it will be easy for us to get the required result. The first and foremost, we have seen here that bx minus ay, bx is equal to ay, in this case bx is equal to ay. So bx is equal to ay. Now we had seen here that bx is equal to ay. Now we will do one thing. We will write x in the term of a, b and y, because we have to solve this equation simultaneously. So we will be writing here x is equal to ay by b. The very first equation we will substitute here x, that is x is equal to a into ay by b, a square y by b plus by is equal to 1. Understood? So we are seeing here that it will be equal to b a square y plus b square y is equal to 1. Now we will just take y common, y a square plus b square is equal to b, y is equal to b by a square plus b square. So we have got the result y is equal to b by a square plus b square. The very first equation is this one. The y is equal to b by a square plus b square. Now we will substitute finally in the x also, and we will get the required result. We will substitute finally first and foremost. So we have written here x is equal to ay by b, x is equal to ay by b. Regarding y, we will substitute the value of y here. So x is equal to a by b into y. Y is b by a square plus b square. So x is equal to a by a square plus b square. So we have got the two results. X is equal to a square plus b square, x is equal to a by a square plus b square, and y is equal to b by a square plus b square. So we have got the result of x and y in the terms of a and b. Now we will see here how we are writing here. Suppose in the case of the natural numbers, we will put here then so we had seen here that one complex number is z is equal to a plus a by, and the second complex number z1 is equal to, in the term of x we will write here a by a square plus b square minus I into y is equal to b by a square plus b square. So we have seen here z and z1, and if we will multiply a plus ib, that is z into z1, we will get the result here 1. Similarly, if we will multiply z1 into z, vice versa, we will get the same output or the same result. So this establishes the relationship, that is z into z1 is equal to 1 and z1 into z is equal to 1. So we have got the relationship. It is quod erat demonstrandum, QED. So this is the basic. This is basically, it is termed, it is defined as the existence of multiplicative inverse. If we are multiplying any two complex numbers in the such as z into z1, and we are getting the output as 1. Similarly, if we are trying to multiply z1 first and then z, and we are getting the same output as 1, then we can say, then it is stated clearly that there is an existence of multiplicating inverse whose product of two complex numbers is 1. This we had seen here. So secondly, we will be moving to the next topic, that is division of the complex numbers. That is division of the complex numbers. Now we are moving to division of the complex numbers. So we are moving to division of the complex numbers. Division of complex numbers. Suppose we are having the two complex numbers z1 by z2. In the case of division, we are writing the numerator on the top side and the denominator on the bottom side. and we are separating the numerator and the denominator by a hyphen sign or by, that is known as by, that is z1 by z2, and we are dividing it. We can write here also, that is z1 into z2 inverse. We can write here z1 into z2 inverse, because z2 inverse is 1 by z2, and we had already calculated the inverse sign here, which we had seen also that or the multiplicative inverse of z is denoted by z1 or 1 by z. Okay, so z is the multiplicative inverse of z is z1 or 1 by z. So find the multiplicative inverse of 1 by 3 minus 2y. So we had seen here how we are calculating. Suppose in the case of example z1, we are writing here z1 is equal to a1 plus ib1. Similarly, z2 is equal to a2 plus ib2. So here we have written here z1 and z2 and we had seen here that z1 by z2, a1 plus i1, a2 plus ib2, z1 by z2. We can write here z1, we can write here a1 plus ib1 into 1 by z2 into 1 by z2, a2 plus ib2. Understood? We can write here z1 by z2 is equal to a1 plus ib1 into 1 by a2 plus ib2, 1 by inverse, that is 1 by a2 plus ib2. That is, we can see here, we can write a1 plus ib1 inverse. We can write the formula is inverse. The formula is, suppose we have to write the inverse formula, we can write here, that is z inverse is equal to, first of all, a by, that is equal to, z inverse is equal to a by a square plus b square. Formula, we are writing the formula here, a by a square plus b square plus I into minus b by a square plus b square. That is the basic formula for the inverse. If you have to write the inverse, the formula of this z2 inverse, we can write also here and we can see. So a1 z1 by z2 is equal to a1 plus ib1, a1 plus ib1 into. So we are writing here 1 plus a plus ib, that is a2 by a2 square plus b2 square plus I minus b2 by a2 square plus b2 square. So we had seen here, we had written here also how we are calculating. So we had seen here z1 by z2, finally z1 by z2, it is, we have to multiply this a1 plus ib1 separately. We have to multiply a1 plus ib1 into a2 by a2 square plus b2 square. Then we have to multiply this one by this. Then we have to take I as a separate and we have to bifurcate, or we have to break that particular number into two parts. One part will be the real part and the second part will be the imaginary part, which we had seen earlier also. So it is basically, we can write here z1 by z2 is equal to a1 plus a2 plus b1 by b1 into b2. Okay, a1 into a2 plus b1 into b2 by a2 square plus b2 square plus I, similarly a2 minus b1, a2 b1 minus a1 b2 by a2 square plus b2 square. So finally we had got the output as the division of the two complex numbers, which we can see that we can multiply the particular complex number with the other complex number by its inverse. So we had finally got the result as this one, a1 into a2 plus b1 by b2 by a2 square plus b2 square plus I a2 by b1 minus a1 b2 by a2 square plus b2 square. So this is basically the division of the complex number. Now we will move towards the next topic, that is entitled as conjugate of the complex number. Conjugate of a complex number. We will see here the conjugate of a complex number. Basically, the conjugate of the complex number comprises of various type of properties. The properties which we had studied with addition, subtraction, those particular properties are only applicable for the addition and subtraction. As far as the properties associated with the conjugate of a complex number is considered or concerned, in that case we have to check or we have to establish each and every complex number and their properties. That will be feasible. So we will be seeing mechanically the conjugate of a complex number one by one. The conjugate of a complex number. Conjugate of a complex number. Suppose we are writing here z1 is equal to a plus ib. That is the first complex number z1 is equal to a plus ib, and the second complex number is z2, which will be entitled as a minus ib. So the z2 which we had written as a minus ib, it will be the conjugate of z1, that is a plus ib. So that is basically the conjugate of z1. Here sign differs. Suppose if we had written z1 is equal to a minus ib, in that case the z2 will be a plus ib, which will be entitled or which will be defined as the conjugate of z1. In this case, basically the sign differs. The method of operation, suppose the addition we had used in the first case, in the second case we have to use subtraction. So that is basically the difference. In the both the cases, only one difference will be there, that is basically the method of operation. In the case of BODMAS, bracket of division, multiplication, addition and subtraction, in this case we will see that only plus and minus sign changes. That is basically the very important difference between the, you can say, the z1 and z2. And because of this property, because of this inherent property, we have to establish the various type of relationships in the case of complex numbers. So we will be seeing slowly and mechanically. So z conjugate and f of this conjugate, it will be z conjugate. Suppose let z is equal to a plus ib. So z conjugate, we had already seen the sign differs, a minus ib. Now again the question arises here. Again there is a conjugate. They are asking, the question is demanding the conjugate of z. That will be again this sign differs. Basically this is this. Now if we are just using double sign here conjugate, it will be a plus ib. So z is equal to z conjugate of z and the conjugate of double conjugate of z. That is basically a plus ib. The second property is z plus z conjugate. So z plus z conjugate. Suppose z is equal to a plus ib and the z conjugate is a minus ib. In this case, if we are adding both the complex numbers, we are finding here it will be 2a. 2a, it states that it only consists of real part, imaginary part is 0. That is 2 real part of z. It is 2 real part of z. Z we had seen here. Z we had taken z equal to a plus ib. So 2a, that is only real part is there, imaginary part is this one. So 2a, that is 2 real part of z. That is basically the thing which we had established. Now we are moving to the, it is the first property. It is the second property. Third property is z minus z bar. Z minus z bar. In the case of z minus z bar, first and foremost, z minus z conjugate of z. So we will be saying here a plus ib minus a plus ib. It is 2 of imaginary part of z. So if we have to subtract any complex number with its conjugate, in that case we will see we are getting as an output as twice of imaginary part of the z, which we had already stated, z is equal to a plus ib. So that is basically the third part. Third property is, if first property is double conjugate of z will be z only. Second property is, if we are adding the complex number with its conjugate, then we are getting the twice of real part of z. Third property is, if we are subtracting any complex number with its conjugate, then we are getting the imaginary part of the z, the twice of the imaginary part of the z which we had seen, we had checked also. Now we will be moving towards the other properties which are of vital importance, and those properties will be helpful. It is basically, you can say, acting as a simple machines through which we are making our work convenient and easier. This modus operandi will be easier, will be helpful for us to solve any kind of complex number which is consisting or comprising of the conjugate section. The fourth part is z is equal to z bar. In this case, z is purely in suppose if z is equal to z bar, so if a plus ib is equal to a minus ib, in this case we will see here it will be basically 2ib is equal to 0. So ib is equal to 0. ib is equal to 0 and z is purely real. So in this case we had seen z is equal to a plus ib. If the imaginary section ib is equal to 0, then we can see or we can state clearly that the complex number, it had been transformed into real number, that is real part is only existing, so complex number is 0. So real part is only existing, so that particular complex number had been transformed into a real number. The fifth one is z plus z bar is equal to 0. If in the case z plus z bar is equal, z plus conjugate of z is 0, in that case we can establish that it is purely imaginary. So we will see here, in this case, suppose it is a plus ib and it is minus a minus ib. Understood? If it is 0, in this case we will see in such a cases, therefore we can see that this is particular. Suppose in this case a plus ib, z is equal to, we can see here z is equal to minus of z bar. We can write here like this. So a plus ib is equal to a plus ib, it is basically minus a plus ib. Understood? So it is basically, we can see here, we can write here z is equal to minus of z bar. So first of all, z bar is equal to a minus ib. So a plus ib is equal to minus a and plus ib. Understood? So it will be equal to z is equal to minus of z bar. Z is equal to, it is z is equal to z bar. So a minus ib, and if it is minus of z, so in this case it will be minus a plus ib. It will be minus a plus ib. So it will be a plus a, 2a is equal to 0. A is equal to 0. So we had seen here that real part is 0. That is real part of complex number is 0. If it is 0, suppose if it is 0, so only imaginary part exists. So we can say here z plus z bar, if it is 0, then only complex number is purely, it is imaginary. That is established. So till now we had came across fifth properties. We had came across 5 properties and we had seen or established also. Now we are moving to the product of complex number with its conjugate, and we will verify the result also. We will verify the result also. So in this case, if it is z into z conjugate, suppose z is equal to a plus ib, so z conjugate will be equal to a minus ib. If we are doing the multiplication part, a plus ib into a minus ib, that will be equal to a square minus ib the whole square. A square, it will be a square minus b square, a plus b into a minus b, and minus I square is equal to minus 1 plus plus b square. It is a square plus b square. That is, we can say it is basically, we can say it is a square plus minus ib the whole square. Understood? As real part का whole square plus imaginary part का whole square. Understood? This is real part, this is imaginary part. This is real part conjugate of that is real part and imaginary part ka whole square. And if it is given like this, that is seventh property, it is sixth property, seventh property. If it is z1 plus z2 whole conjugate, z1 plus z2 whole conjugate. So if we are writing here, z1 is a plus ib plus x plus iy. So it is basically a plus ib plus x plus iy. Understood? So we can add here also a plus x and plus I b plus y. We can write here like this: a plus x plus ib plus iy. So it is basically as per the theorem which is stating, it is basically z1 bar plus z2 conjugate. So z1 conjugate, it is a plus ib. Now z, we have seen here a plus ib. Z1 conjugate will be a minus ib plus z2 conjugate x minus iy plus x plus iy, it will be x minus iy. Understood? So it is basically a plus x, and if we are taking minus I common, b plus y. Understood? So it is basically z1 plus z2. The whole conjugate will be a plus x minus I b plus y. So this part and this part, these two parts are equal. So we can easily say the addition of two complex number and its conjugate will be equal to the conjugate of the first term plus conjugate of second terms. That is basically the seventh property. Similarly, we will see the subtraction of the two complex number and its conjugate will be equal to the conjugate of first part minus conjugate of second part. We will see and establish here also. So we will see here also the eighth property. The eighth property is somewhat similar, but it is holding more gravity as comparison to first or fifth property. It is holding more gravity. The eighth property is z1 minus z2. The conjugate of z1 minus z2 is equal to z1 minus z2. This we have to establish, and we will see here also. So z1 minus z2 is equal to z1 minus z2 separately. So in this case, if you want to define it, this is mathematically we have seen. If you want to define it, you can say orally. In that case, we can say here the difference of two complex numbers and its conjugate will be equal to the conjugate of first term and the conjugate of first complex number minus conjugate of second complex number. We will see here also, if we are taking LHS here, z1 is equal to a plus ib minus x plus iy. Understood? So it will be a minus x. It will be a minus x plus I b minus y. So we had seen here its conjugate will be equal to, now its conjugate will be equal to a minus x minus I b minus y. This is the LHS part. Now coming to RHS part. RHS part is conjugate of first term, that is a plus ib, that will be equal to a minus ib. Directly we are substituting. Second part, z2 x plus iy, that will be x minus iy. Now if we are solving the expression, it will be like this: a minus x plus I y minus b. So if we are writing here also, it is, if you are taking here plus I common, minus b plus y. Understood? So this is basically that. So we had seen here how the LHS equal to RHS, which is stabilizing our relationships. So far we had covered the 8th property. Now we will be switching over to the 9th property. That is the product of the two complex numbers and its conjugate will be equal to the product of conjugate of those two complex numbers separately. We will be seeing here, and it will be easier for us to establish also. So it is the ninth property. Ninth property, it is somewhat complex here, but it is also holding the similar magnitude as that of seventh and eighth property. Coming to ninth property. The ninth property is, it will be equal to Z1 Z2 conjugate is equal to Z1 Z2. This is basically, we had to establish a relationship between the two complex numbers and its conjugate. Mathematically stating, if we are taking two complex numbers and if we are taking the product, or if we are multiplying those two complex numbers, and after that, post that, if we are checking the conjugate of those two complex numbers, which will be equal to the product of the conjugate of the two complex numbers taken separately. So it will be, suppose Z1 is equal to A plus IB, suppose, and Z2 is equal to A minus A1 plus IB1, or X plus IY, you can take X plus IY. So we have to multiply. So it will be equal to A plus IB, X plus IY. So AX plus AIY plus IBX plus I square BY. It will be, understood, it will be AX plus I square equal to minus 1. AX minus BY plus I AY plus BX. And its conjugate will be equal to AX minus BY minus I AY plus BX. That is equation number 1, LHS. Now coming to RHS separately. Z1 is equal to A plus IB. Its conjugate will be equal to A minus IB. A minus IB RHS. We are writing here RHS. A minus IB into X minus IY. AX minus AIY minus IBX plus I square BY. So AX minus BY, now I common, BX plus AY. So we had seen here these two equations, AX minus BY minus I BX plus AY. So we have seen here LHS equal to RHS. We had established also, mathematically stating, if we are taking two complex numbers and we are multiplying both the complex numbers together, post that, if we are taking the conjugate of those, that particular product, which will be equal to the product of two complex numbers, the product of the conjugate of the two complex numbers taken separately. That is basically the ninth part. And these three properties, basically 7th, 8th and 9th, these three properties, these are holding greater magnitude or greater gravity as compared to the other properties which we had seen earlier. Now coming to the 10th property, it is also a very vital property which we will be seeing here. So it is 10th property is somewhat like division. 10th property is somewhat like division. 10th property is somewhat like division. So here it is, Z1 by Z2 conjugate, whole conjugate is equal to Z1 bar by Z2 bar. That is conjugate which we are taking. So we have to check here. A1 plus, if we are taking Z1 into Z2 inverse, which we can write here also, Z1 into Z2 inverse. which we can write here. Suppose if we are taking here Z1, we can write here Z1 into Z2 inverse. Suppose we are taking Z1 is equal to A plus IB, Z2 is equal to X plus IY. Understood? So Z2 inverse, that is basically Z2 inverse is equal to Z2 inverse. Find the multiplication. Suppose it is written here X Z is equal to X plus IY. So its inverse will be equal to, basically A by A square plus B square. So Z2 inverse the formula is A by A square plus B square. Understood? Plus I B by A square plus B square. Understood? So it is basically the formula, and we will be writing here similarly like that only. Suppose if we are taking Z1 it is similarly we will be taking A plus IB into Z2 inverse. Z2 inverse is we have to take this part X plus IY. So we are by back substitution it will be X by X square plus Y square plus I. B part is Y by X square plus Y square. Understood? Understood? So that is basically this. This is the part that inverse of Z2 inverse is this one. So if you are multiplying it again, it will be equal to AX by X square plus Y square plus now again AIY by X square plus Y square plus IBX by X square plus Y square. I square is minus 1 minus BY by X square plus Y square. So we are taking the right terms, the real part together. That will be AX minus BY by X square plus Y square. Understood? Now I is common. AY plus BX by X square plus Y square. So this is basically AX minus BY by X square plus Y square plus I AY by BX by X square plus Y square. Now, taking the right hand side, we will check the right hand side and we will try to equate LHS and RHS, which will be establishing our relationship, quod erat demonstrandum. So, moving towards the RHS side. RHS side is somewhat different, and we will be stabilizing also the relationship. That will be easier for us. So, Z1 and Z2. Suppose Z1 is there and we are writing here as A plus IB. So Z1 inverse is, it will be equal to A minus IB into conjugate of Z2. It is X minus IY. That is basically the Z2 conjugate inverse. That is basically 1 by X plus IY. X minus IY, sorry. We are writing a Z2, we can write here as conjugate is X minus IY. We can write here in the multiplication form, that is inverse of 1 by X minus IY. Now, we will be solving those two equations which we had seen also earlier. That is A minus IB into. What is the inverse of 1 by X minus IY? That is basically, first of all we have to check X part. It is X. Now A plus IB, that is X square plus Y square. Understood? Now plus I P part, that is Y by X square plus Y square. We can write here minus because the minus part is here. Now we have to again multiply it similarly. That will be equal to AX by X square plus Y square. Minus plus, again it will be minus AY by X square plus Y square. So the same thing we have to follow here also, and eventually or finally we will be getting the result as LHS equal to RHS. So we have seen here how the division part, the conjugate of the division of two complex number will be equal to the division of conjugate of first part and this conjugate of second part, which we had seen here. That is LHS equal to RHS. So far we had seen the 10 properties associated with the conjugate of the complex number, and we had seen how we had solved some of the numerical problems associated with the complex number, and we will see 2 or 3 examples which will render more transparency, and it will then post that it will be easier for us to easier for us to understand the basic concept associated with the complex numbers. So we will be seeing 2 or 3 examples which will render more transparency here. First and foremost, we will be dealing with the inverse part. That is basically, suppose if any complex number is there, if it is written like find the multiplicative inverse of z is equal to 3 minus 2i. We have to calculate here z inverse. We can write here 1 by 3 minus 2i. We have seen here z inverse is equal to a square by a square plus b square plus I b square by a square plus b square. Understood? So we had seen here that z inverse is equal to 1 by 3 minus 2i. That is, a is 3 here, b is minus 2 here. So we have to substitute the values of a and b in this particular expression, and that is basically the inverse part. Solving the inverse part, a is 9 by 4 square plus 16, 25 plus I, it is 4 by 9 plus 16, it is 25. Understood? So we have seen here, it will be basically, and we had also came across the various parts here. It is basically 3, that is a square, a by, so it is basically a, not it is a square, it is a. So it will be 3, and it will be b part, it is minus 2. So expanding more, we can write here that z inverse is equal to a square plus b square, 9 plus 4 it is. 9 plus 4 it will be 13. Sorry, 13, and it is also 13. So it will be 3 by 13 minus I, and it will be plus IB. That is, it is basically equal to a 1 by z is equal to minus of I. That is I, and it will be 2 by 13. That is z inverse. So we had seen here how we had calculated the z inverse of the complex number, and so far we had discussed the addition part, the properties associated with the addition of the complex numbers, the subtraction part, the properties associated with the subtraction of the two complex numbers, multiplication part, we had seen thoroughly the various properties associated with the complex number, the multiplication of the two complex numbers, the multiplicative inverse we had seen, that is basically the formula of z inverse is equal to a by a square plus b square minus ib by a square plus b square. We had seen also, and we had solved the numerical problem in which we had applied the same formula. Coming to the conjugate of the complex number, we had seen the conjugate of the complex number is basically, it is defined as the sign changing. The changing of the sign takes place. Suppose z is equal to a plus ib. If we have to find the conjugate of a complex number, we can write here z is equal to a minus ib. That is basically the definition of the conjugate of the complex number. Parallel to this, we had seen the various properties associated with the conjugate of the complex numbers, and we had seen also, and we had came across the various properties. We had established also the relationships between the LHS and RHS. We had seen, and we had verified also the Q derived instrumentum part. So far we had covered the 60% topic of the complex number, and I'm checking, and if any issue is there, we will try to solve it as soon as possible. So I'm requesting, if any problem is there, if any issue is arising regarding solving of the complex number, you can just ping me. I am available here 24 bar 7, and I will try to resolve the query within the shortest stipulated time. And in the next class, we will be seeing the various forms of the complex number, how we are representing the complex number in the polar form or Cartesian form, in the coordinates. In the Cartesian means coordinate form. How we are representing any complex number in the Cartesian form, that will be more beneficial. We will try as soon as possible to cover this topic. And so for today, it is enough. And we will be seeing the other part of this complex number in the next class. Till then, thank you.